one easy thing to observe is for P complete problem that say L is P complete, then if that problem is in NC, that is there is an efficient parallel algorithm for a P complete problem, what it would mean is that every problem in P has a efficient parallel algorithm. So, NC will be P. So, if you believe that NC is not equal to P, then P complete problems cannot have an efficient parallel simulation. And similarly, P complete problem, if it is in log space, then every problem is in log space. Okay, so we believe that log space is different from P, and hence P complete problem cannot be solved in log space, and P complete problem cannot be solved in NC, cannot have a parallel simulation. Okay, so in this sense a P complete problem is hard. Okay, it's in the sense of hard to parallelize. Okay, this is the meaning of P hardness. So let's introduce it, and again circuits will come to rescue. So circuit evaluation is the problem we will define. So circuit evaluation is the problem of given a circuit and an input, does it accept it? So is Cx equal to 1? So C is a circuit with n inputs, 1 output, and Cx is 1. Okay, so basically circuits with accepting inputs, that is what circuit evaluation consists of. It basically just is asking whether a circuit and an input is 1. Okay, so intuitively you have to compute the whole circuit for this, and we will show that this is P complete. This is a P complete problem. Circuit evaluation is P complete. So first is that it is in P. Why is it in P? Well, because given a circuit you can obviously compute it, given a circuit and an input. So given C comma X, it is easy to simulate, to compute Cx by a Turing machine, right, in polynomial time. Efficiently you can check whether you can compute C of x and then check whether it's 1 or 0. That's the easy part. So more interesting thing is P hardness. Why is it P hard? So why can you reduce every problem in P to this in log space using a implicitly log space reduction? So let L be in P with Turing machine M of time complexity n to the c, where x length is n. So, in other words, let L be a problem which is solvable in polynomial time. C is an absolute constant. So, polynomial time solvable problem L and Turing machine solving it. Let us start with this. So, essentially you recall Cook-Levin reduction, right? That reductions basically converted every step of the Turing machine computation into logical gates, and if you go over all the steps, then ultimately it is giving you the circuit you want. So, as in, just let us recall, so as in Cook-Levin, we can assume M to be oblivious and translate the step, the ith step basically which maps configuration Ci to Ci plus 1, translate the ith step to a formula. And this we can see as a constant size circuit. So, this implies that each step is a constant size circuit. Let us call it Ci. So, this is the major thing we are recalling from Cook-Levin. Once you understand this, then now what happens is Turing machine M has many steps. It has n to the c many steps, and every step is just a computation of a constant size circuit. So, you can join them together and you get a big circuit still of size polynomial. Okay, that is faithfully simulating what M was doing. So, since number of steps is less than equal to n to the c, in fact n to the c log n, this means that we get circuit C of size n to the c log n, exactly simulating M. Right. Moreover, okay, this is all fine. This we understand that Turing machines can be converted into a circuit, but why is it a log space reduction? Right. That's the only thing missing. So, the ith circuit Ci, this can be determined using or given, can be determined easily. Basically, this is from control of M. and the ith head position independent of x. Right? That's the point of oblivious. It doesn't depend on x, it only depends on length of x, which is n. So, using m's control, finite control and the ith head position, you can compute the circuit Ci given given I and the previous configuration Ci minus 1. Right. So, taking this as an input, you can compute the circuit, and all this only requires so how much space is needed for this? You only need to basically store I. In space at most the length of I, right, which is what is length of I? So, I goes up to n to the c, so it is log n. So, what we have shown is that the problem in polynomial time, which we took as L, this has been reduced to circuit evaluation on X. L reduces to circuit evaluation. So, you just have to compute the circuit, and if the circuit on X is 1, then X is a yes string. Right. So, L reduces to circuit evaluation by log space. By log space reduction, which means that circuit evaluation is P complete. Right. So, circuit evaluation we have shown is a P complete problem, and which means that this problem you cannot solve in parallel. So, this we can now make this conjecture that circuit evaluation can't be done efficiently or can't be parallelized, let us say. Okay, so intuition is that the circuit is already, I mean, although circuit is kind of a parallel algorithm, but for a Turing machine to compute it, it has to go in every part. No part can be, I mean, it cannot be distributed across different processors. Okay, one processor has to go through this. So, it's an interesting problem which is in polynomial time. It's the hardest in polynomial time in the sense of parallelization. If you want to convert every problem into a fast parallel algorithm, then you have to convert circuit evaluation problem. That will suffice. Okay. So, as a corollary, what you get of this from this proof is this problem of circuit SAT. Right, circuit SAT is the problem of given a circuit, whether it has a satisfying assignment. Circuit C, and there exists an X such that it evaluates to 1. The circuit SAT is NP complete. Well, this is kind of immediate, right? So, circuit SAT is clearly in P. Sorry, in NP, because you have to guess, you just guess X. And then compute C of X in polynomial time. So, it's clearly in NP, and 3 SAT reduces to it. Three SAT trivially reduces. Trivially, 3 SAT will reduce to circuit SAT. Okay, so circuit, what we have shown is that circuit evaluation is P complete, where the notion of reduction was implicit log space reducibility, and circuit SAT, when this X is not known, you have to guess it, this is NP complete. Right. So, both these problems are new problems, but they fit very well with the known complexity, already defined complexity classes. And circuits also help to understand NEXP. To study higher classes, like pH, P space, I mean this even before P space you have this sharp P. pH is a question about formulas, so that is again a circuit question. Sharp P is about sharp SAT, again circuit question. P space is about QBF, and we will now move to NEXP. It also helps understand NEXP. So, how is that? So, let us define a NEXP complete problem. Circuits give a natural problem for this I need to define a harder version of circuit SAT, right? Circuit SAT is in NP. For NEXP I have to make it harder. How do we make it harder? We make it succinct. Okay, so C is a succinct circuit if given I in binary, so I is given in binary via n bits. There exists a polynomial in n time algorithm to output the ith gate. let us say the ith gate and its jth edge. So, let me make this I comma j. So, essentially what is the ith gate and how is it connected to its neighbors? So, what is the ith gate and what is the jth edge? How is it connected? Right. So, this local connectivity information is easy to compute, that is what it means. That is local connectivity is easy to find while the graph itself is huge. Okay, it can be of the order of ig or n bits. So, I guess 2 raised to order n or order n square. Okay, so if you look at the number of gates, they are actually 2 raised to n, and the number of edges can be then 2 raised to 2n. So, circuit graph or the circuit tree is huge, but each interconnection can be computed efficiently. Okay, so, local information is easy to compute. This is what a succinct circuit is. And what we can show, the theorem says that succinct circuit set okay, this is NEXP complete. So, succinct circuit set is a circuit set, but where the circuit is given to you in a succinct way, right. So, local connections can be easily computed, there is an algorithm, but obviously the whole circuit cannot be given because it is too large. So, if you can test whether it has a satisfying assignment, then you can solve NEXP. So, let me point out that circuit size is exponential 2 raised to order n, but number of variables is n. Okay, so, number of variables is not exponential, number of variables is just n, but the circuit itself has large size 2 raised to n, 2 raised to 2n size. And so, whether given such a circuit in this local way, can you test its satisfiability? So, this problem is NEXP complete. So, first of all, why is it in NEXP? So, it is in NEXP it is in NEXP because you can guess x. And then you can compute C of x in exponential time. As the size of C is only exponential in n. So let me change some things here. So this is n to the C. Okay, circuit size is n to the C. C is an absolute constant. And then yeah, so you can actually guess x in 0 1 to the n. And for this x, the circuit size is promised to be at most 2 raised to n raised to c for some constant c. Okay, so in NEXP it can be any constant c. So circuits of size 2 raised to n raised to c are allowed, but the information, local information, will be computable in polynomial time, poly n time. Right, that's all what succinctness means. So this satisfiability can be checked once x is given. Cx equal to 1 can be computed. So that part is the easy part. The difficult part is being hard. Why is it hard? So next hardness we will do. We have to reduce any problem in NEXP to that, right? So let L be in NEXP. With M being its exponential time verifier. And input x being 0 1 to the n. Right, so we have the verifier, we have the input, and we have the language in. M is the Turing machine verifier and L is the language, the problem in NEXP. Now, the ith step of the Turing machine, Ci to Ci plus 1 configuration change. This has, so what will this configuration size be? This will be exponential, right? The configuration size is exponential, but so the smallest change from one configuration to the next, this is given by M's control. So that has a constant size circuit. Which is producible in how much time? So you just have to compare the locations. So it will be computable in log of the number of, the basically configuration size in this time, which implies so configuration size is how much? That will be log of the number of steps. right, which is 2 raised to n raised to c, that is polynomial in n. It's polynomial n time. Right, so which means that the configuration graph this configuration graph is or the circuit that you get the corresponding circuit is succinct. Right, which means that we have reduced L to succinct circuit set. So every problem in NEXP via the configuration graph or via this Cook-Levin reduction can be reduced to succinct circuit set. Right, so this is a problem which is NEXP complete. So with this we finished the course. We covered a lot of topics, and to learn more you can do the advanced courses. I hope you enjoyed. Thank you.